Okay.
Physics neural networks.
I was going to.
Yeah.
I thought I might get a chance to make a joke at Shannon's expense, but she's here on time this time, so well done. So today, I have the pleasure of introducing Omelchenko, who is visiting us for 1 week. And well, you've already seen him looking at this title, but he's going to tell us about chimeras and where they live. Anthony, this is for you. This is chimeras.
Yeah.
Same thing.
Chimeras.
You would not really.
Chimeras.
Chimeras.
Okay, but I will call them as I used to call chimera states. Okay, thank you very much for coming here. Michael, once again, thank you very much for hosting me at this wonderful place. My talk will be about synchronization patterns in coupled oscillator networks, and in particular about chimera states. I think not everybody is familiar with these concepts in detail. Therefore, I will start with a brief introduction to the topic. So, first of all, oscillators are everywhere around us. They can be recognized in biological oscillators, neurons, mechanical oscillators, lasers. On the mathematical language, each oscillator is represented as a nonlinear system exhibiting attracting limit cycle. And if such oscillators interact with each other, there are many copies of them, then they tend to synchronize their oscillation rhythms in the form of different synchronization patterns. You are probably familiar with the movies showing how metronomes can synchronize. Then synchronization patterns are known to be useful in the brain, for example, encoding information in working memory, or they can be responsible for malfunctions like pathological synchronization relevant to Parkinson's disease or Alzheimer's disease. Maybe another example which is less known to you are cilia carpets. So cilia are hair-like structures on the surface of cells, and if many haired cells are assembled together in a tissue, then the nearly periodic motion of these hair-like structures can synchronize, and then this synchronized pattern called metachronal wave can play a transportation function on the surface of such tissue, such that some particle can be transported by means of such metachronal waves. So most of this synchronization pattern phenomena can be studied by mathematical simulations for certain models, but in mathematical studies, people usually try to simplify mathematical models as much as possible, and the most simple model used to describe synchronization patterns are phase oscillator models. It is known that phase oscillator models can be rigorously justified by phase reduction for weakly interacting nearly identical self-sustained oscillators. And at the output of such phase reduction, one usually obtains a mathematical model written here, which represents states of each oscillator as a phase, scalar variable, considered modulo 2 pi. From intrinsic properties of each oscillator, one preserves only natural frequency corresponding to rotational frequency of free oscillator, and interaction between oscillators is given by two ingredients. So phase interaction function, which is 2 pi periodic because of definition of the phase, and depends on the difference of phases. There can be other more complicated functions like higher order interaction, but I'm not going to touch this in this talk. And the connectivity structure in the network is encountered in adjacency matrix, which can be also weighted. schematically, if one applies this scheme of phase reduction to study some phenomena in reality, one applies the following linear scheme. So one starts with a real world model, comes to phase oscillator simplified model, and looks for some exotic phenomena. And metaphorically, this approach can be explained as if you have a real forest, then you replace it with a simplified picture like this, or it can be even more schematic like this, and then you look in this forest for most exotic creatures. So I come from Germany. In southern Germany, according to local hunters, one can find such an animal called Wolpertinger. And it is known because it consists of some incongruent, unexpected parts. Some mathematical Wolpertinger was described 20 or even more years ago by Kuramoto and Batoktok in 2002, and it received name chimera state from the paper by Abrams and Strogatz 2 years later. So what is the dynamical state which Kuramoto and Batoktok discovered? It was described in a system of non-locally coupled phase oscillators, which is written here. This is a Kuramoto type model. So you see the state of which oscillator is represented by phase. All oscillators are identical. They have the same natural frequencies. And the interaction between oscillators is due to the product of these two terms. One is sinusoidal term with a very important parameter alpha, which I will call phase lag in the following, and the interaction between oscillators is given in a so-called space-dependent manner. Namely, one assumes that oscillators are ordered on a line such that each of oscillators has its physical position in the space. There is a scalar function g, and the value of this function g evaluated at the difference at the distance between positions of the oscillators gives the value of the adjacency matrix of the coupling strength between oscillators with index j and k. This assumption about physical positions of phase oscillators helps to visualize behavior of chimera states for different system sizes, and in particular in the following I will always show that positions of oscillators are in the interval from -pi to pi, but the number of points corresponds to size of the system. And another ingredient which was introduced by Kuramoto and Batoktok in this model were periodic boundary conditions. So the distance is measured with respect to periodic boundary conditions. And due to all these ingredients, if you look carefully at this model, you recognize that all oscillators are identical. They interact with their neighbors identically. That means they are indistinguishable. But anyhow, for certain perturbations in this system, in this homogeneous system, some spontaneous symmetry breaking can occur, such that a dynamical pattern, which I will demonstrate you now, can appear. So this is famous chimera state pattern. So you see a homogeneous system splits in two subparts. In one part, all oscillators are phase locked and they rotate with nearly the same frequency. This is synchronized or coherent domain of a chimera state, and the rest of oscillators drift with respect to each other. They move kind of incoherently, asynchronously. And because this state composed of coherent and incoherent parts occurs in homogeneous system. This was like unexpected behavior, similar to Wolpertinger with the incongruent parts. So coherence and incoherence coexist simultaneously. So that's why this state was called chimera state. Many people, including me and my colleagues in Berlin, studied chimera states numerically, in particular for relatively small system sizes, like in this case, I think 30 or 40 oscillators, performing statistical analysis of chimera states. We could find that chimera states are chaotic patterns, so they have many positive Lyapunov exponents. Then if one looks at the position of a chimera state, which in principle can emerge at any position on a ring, there is no preferred position on a ring. But then if chimera emerges, it can exhibit some random work motion along the ring. It has wandering position, and moreover, for finite n systems, chimera states also may have finite lifetime, such that you can observe chimera state for sufficiently long period of time, and then it spontaneously collapses to completely synchronous state, which stably coexists in the same system. This part of work was done mainly numerically, but there is also another way to chimera states which allows to analyze them more analytically, writing some formulas, performing bifurcation analysis, and this approach is available in the continuum limit case when you look at the chimera states behavior for infinitely large system sizes. So what one can do in this case, one first can notice that increasing number of oscillators in the system, one gets rid of chaoticity, of wandering position, finite lifetime, and chimera for increasing system size looks like qualitatively the same pattern, but with the increasing density of points populated coherent and incoherent domain. And this suggests the idea that in the continuum limit, one can represent the state of the chimera generating system by probability density function, which tells you what is the probability to find oscillator with value theta at position x at time t. And then there is a standard way how one can write evolution equation for this probability density function. This way is explained here. So I rewrote this system, original system of equations in the following form, as if each oscillator interacts with some mean field, Wj, and this mean field is defined by this sum. So these two lines are identical to the system on top of the slide. And then if you assume that the state of the chimera state indeed is represented by this probability density function, this sum can be replaced with the integral. So this is just Riemannian sum is replaced by the integral. And if you look at this equation, if there is a single particle driven by the mean field W of j, there is a Liouville equation describing evolution of probability density. So in such a way, you can come to this type of continuity equation describing evolution of probability density. Now, this equation is nonlinear. It has quite complicated solutions because they are measure-valued functions. And in general, it is not much simpler to analyze this equation than original system. But there is one trick or fact, mathematical fact, which helps to simplify analysis of this equation. And it follows from the famous result reported by Edward Ott and Thomas Antonsen in 2008 in this famous paper written by them. And what was formulated in this paper, I tried later to translate to chimera states. And this Ott-Antonsen result translated to chimera state system can be reformulated in the form of proposition. So what does it mean? Every probability distribution rho is 2 pi periodic function of the angle theta. That's why it can be represented as a Fourier series. And what Ott and Antonsen found, there is a special form of such Fourier series where nth coefficient of Fourier series is given by nth power of the same function z. And this ansatz gives exact solution to the continuity equation which I wrote in the previous slide, provided this function z satisfies such an integral differential equation which I will call Ott-Antonsen equation. So this equation is nonlinear. It contains parameters of the original system such as natural frequency, phase lag alpha, then coupling kernel describes non-local interaction. And what is nice about this equation, chimera state, they are represented by rotating wave solutions of this form, which lies on the Ott-Antonsen manifold. That means if you would like to the leading order understand properties of chimera states, you can look at this equation, insert this ansatz, and find how amplitude and collective frequency omega depend on system parameters. Nice thing, there is no any chaoticity in the continuum limit, no wandering positions, so these are pretty regular solutions, so they can be found using Newton solver, for example. And one can also perform linear stability analysis of these states with respect to this equation, and the information about linear stability determines you linear stability of chimera states. So in particular, if one takes the very simplest non-local coupling, like containing only the leading non-constant spatial Fourier harmonics, then one may ask what are parameters A and alpha in this model for which you can find chimera states. And applying the approach which I described to you, one can find such a bifurcation diagram where, for example, 2 different types of chimera states are identified in this model, and parameters for which this chimera state is stable are shown in hatched region. Parameters for which this anti-phase chimera state is stable are in shaded region, and moreover, from the linear stability analysis, one can also identify the reasons of instability, like saddle node bifurcation, Hopf bifurcation in red, and pitchfork bifurcations in blue. Also, one can identify coexistence of several chimera states. The approach which I briefly described here is applicable not only for chimera states living on a one-dimensional grids, but it can be applied to more complicated models. For example, if one considers two-dimensional grids or three-dimensional grids, one also can find chimera patterns, and they assume more complicated structures. So on linear array on a ring, we observed only such 2 chimera states, but on a 2-dimensional grid, one can find states where, so I use here color to represent phase. Chimera assumes a shape of stripes, spirals, spots. In a 3-dimensional case, they can be even more complicated, like coherent ball, tube, planes, spiral rolls. So all these can be done using the mathematical analytical approach which I just introduced you. So this was a kind of end of my introduction. Before I move to the main part of my talk, where inverse problems are formulated and mathematical tools have to address them, are there any questions about chimera states and model where they were first observed?
You said chimera states can happen everywhere, but in most of the pictures they happen on the side of the rectangle.
I intentionally center them in such a way that they look symmetrically. But of course, any copy of the same pattern shifted by 1, 2, 3 points in the right or in the top direction is possible. Oscillators are indistinguishable. This is only...
I would expect that since you have exponential decay...
there are periodic boundary conditions.
Yeah, okay.
Any other question? Yeah?
Just with the classification diagram in the previous slide.
Yes?
So where there's a hash and the shaded part coexisting, are there 3 chimera states happening? Because you said there's coexistence.
Yes, here in this overlap of shaded and hatched region,
Yeah.
you can find both this and this chimera state depending on initial conditions.
All right, depending on initial conditions. So is there like a weird doubling kind of thing? As like, is it nested? So if you go deeper, you can find smaller regions that have.
It depends on which type of non-local coupling you use. So for this type of non-local coupling generated by such a function, I would say only these 2 types of chimera states are observable. But if you take a coupling function with more spatial Fourier harmonics, you can obtain other chimera states.
But you need to add another Fourier harmonic to get
Yeah.
another set.
Yeah, but of course one has to check stability of the states. Okay, maybe I will proceed further. So the idea which I would like to advertise in this talk is that beyond stability analysis, bifurcation analysis of chimera states, continuum limit approach can be used also for another type of problems, namely inverse problems where one wants to reconstruct the model where chimera states is observed from the observation of chimera state and using minimal information about observed chimera state. And this is possible based on the fact that probability density function, which represents chimera state, it combines inside of it some information about local dynamics and local properties of the oscillators. In order to extract these local properties of the oscillators and local dynamics quantifiers from the probability density function, I propose to use famous ergodicity property. So ergodicity property tells you that if you have some time average of the phase, so angular brackets represent time averaging, then you can replace it with averaging over probability density. So roughly speaking, ergodicity means this identity. Note that on the right-hand side, I kept time averaging only because probability density have also explicit dependence of time. Would it be without explicit dependence, it would be a kind of time averaging is replaced by integral over probability density. And using this approach, for example, one can define local quantifiers of the dynamics of any partially synchronized pattern in a network of phase oscillators. For example, for chimera states, which I show here as a space-time plot. One global quantifier is a global order parameter, Kuramoto order parameter, written here. It tells you how synchronous is the state of the network at each time moment. But one can also present some local dynamics quantifiers which refer to dynamics of individual oscillators. One of the simplest is effective frequency. This is just time average of phase velocity. And another local dynamics quantifier which I will use in the rest of my talk is local order parameter. It is defined here using global order parameter, and it tells you, roughly speaking, how frequently your oscillator J sleeps with respect to the global order parameter. So by definition, this quantity is complex. So here is its magnitude and argument shown for this chimera state, and a kind of exemplifying plot for effective frequencies for this chimera state is shown here. So what I would like to use, I would like to use ergodicity property to calculate these quantities, these time averaged quantities, using a solution of the Otto-Antonsen equation. And as you will see, at the end, I obtain relations which connect system parameters and this time averaged local dynamics quantifiers. And later, these relations will be used to reconstruct the system where chimera state is observed. So these are relations which can be rigorously derived, and for the sake of your convenience, I colored in red local observables, these time averaged quantities. System parameters are colored in blue. So you see there are three sets of parameters. Yeah, in fact, the first and second type of relations, which I will call statistical equilibrium relations, they hold for every indices J, but these third line relations, they hold only for those indices J for which magnitude of local order parameter is less than 1. And what is important about these relations, they are valid for any chimera state, observed for any coupling function, any phase lag, any natural frequency. So a kind of for any partially synchronized pattern, stationary pattern, which you can find in system of non-locally coupled phase oscillators, these relations are fulfilled. The only issue is, you remember probably definition of effective frequencies and local order parameters. They are for infinitely long time averaging, and this rigorous result holds true only for infinitely large systems. I would like to show you that it can be still used for relatively smaller system sizes, not infinity but smaller, and for time averaging over reasonable amount of time. And for justifying this approach, I show you results of numerical check how long these statistical equilibrium relations hold true if you replace your time averages with time averages over time t, and if you take certain finite system size. So what I calculated mean discrepancy in the statistical equilibrium relation 1, relation 2, relation 3, and plotted them as a graph. And you can see that if you go to system sizes around 1000 or more, then the accuracy of relations becomes already very good in the sense the discrepancy is very small if provided averaging time is not infinite but only 1000 time units. And the idea is these relations, they remain valid for relatively small averaging time and for not extremely large system sizes. So what can we do with these relations if we use them in this case when system size is 1000 or more and averaging is over 1000 time units? Can we use these relations to tell something useful about the system which we look at if we find chimera state in this system? So roughly speaking, I would like to use these relations to answer the practical question. Given a chimera state without perturbing your system, can we reconstruct system parameters? So natural frequency of all oscillators, phase lag, coupling function. Here is a graphical representation of the second part of my talk. So roughly speaking, if we observe chimera state, can we tell what is the forest where it can be found, where it lives? Okay, you may ask me why I am going to use statistical equilibrium relations if there is a general approach how to reconstruct system parameters. So one can take equations where chimera state is observed, calculate discrepancy in each equation, and look at the parameters as a minimizer of this functional. This is a valid approach, but if you use real experimental data, they are always noisy, therefore it's difficult to calculate derivatives. Then if you go to larger and larger system sizes, then you need to evaluate larger and larger amount of data in order to calculate this functional. And third issue is that the entire trajectory, so phases of all oscillators are needed to apply this approach. And in the rest of my talk, I would like to show you that using statistical equilibrium relations, one can solve the same problem, but using only this small set of effective frequencies and local order parameters. So all these parameters can be reconstructed. And of course, because method is already a bit based on numerically justified assumption that statistical equilibrium relations are valid for finite n systems and finite time averaging, I can't offer you rigorous proof of these results, but I can show you that the method which I would like to propose works in different settings and it works reliably well. So for this I will consider three types of coupling functions for which chimera states were observed. So so-called top hat coupling with sigma representing relative coupling range, then exponential coupling which decays with the speed determined by parameter kappa, and this cosine coupling which I showed you. For example, picking some fixed value of sigma and phase lag alpha and plotting statistical equilibrium relation 1, namely plotting, first calculating effective frequencies, local order parameters, and then plotting omega j versus this ratio in the plot as a circles, I see that everything, all points lie almost along the line. And this is not a surprise, because if you look at the formula, you see that this relation is linear. And by linear regression, you can find, for example, this parameter and the difference between omega small and omega capital. So from the first set of relations, you can already reconstruct natural frequency. Then I also want to use the remaining two sets of relations, 2 and 3. And I want to approximate coupling function with some finite Fourier series. That means I will look only at a finite number of coefficients Cm in this Fourier series. And because chimera states in all these examples which I showed were observed with coupling function which is even, so the interaction to the left neighbors is the same as interaction to the right neighbors, I use cosine Fourier series. And then the idea to use statistical equilibrium relations 2 and 3 will be as follows. I insert this ansatz in the definition of expressions xij, which were given a few slides before. And then I obtain that if I calculate local order parameters, zeta j, then, and I know positions of all oscillators, xj, then I have two sets of relations where coefficients of Fourier expansion are present and phase lag. So I think I gave somewhere definition of beta. Yeah, it was here. So beta is nothing else but just linearly rescaled phase lag alpha. And now the idea is to construct two functionals which measure a kind of mean discrepancy in the statistical equilibrium relation 2 and 3 and use them to reconstruct all coefficients Cm and beta. So how it is done, I wrote here. So roughly speaking, in the first line, I wrote discrepancy in the second relation, so this relation, and I assume here that we don't look at parameter beta at phase lag, but we look only at parameter Cm only. This is a least square optimization problem which can be solved explicitly, and one can obtain these expressions Cm tilde of beta explicitly. Then I insert these expressions in the second function where I estimate mean discrepancy in the set of relations 3. And this is a function depending on beta, and I want to find its minimum. And this will be my prediction or reconstructed value of the phase lag. So in this plot, I show you how this approach works for global minimum search for a particular chimera state. Notice that this is a logarithmic scale, so you see that minimum, which is close to exact value, shown with dashed line, corresponds to several orders of magnitude smaller value. So you can see that this minimum search can be done reliably. And then since we from the first step already found this function Cm tilde of beta, the found value beta can be inserted, and coupling function can be reconstructed. This is a kind of general approach. Now how it works in the case if you take chimera state with 2048 oscillators and approximating coupling function with 10 Fourier harmonics. So this is top hat, exponential cosine coupling. So in the middle and right figures you see nearly perfect results. Here you see some oscillations, but this is famous Gibbs phenomenon. So if you would like to approximate the top hat function with 10 Fourier modes, you will obtain nearly the same curve. So the accuracy in this particular case is very well. Now you may ask me, you showed just 3 examples. Does it work for other system parameters? Here is a numerical answer to this question, namely, if I fix for top head coupling certain value of coupling range, like 0.7, and start to vary phase lag parameter, and plot reconstructed values versus input values. So you can see that the dots lie almost on the diagonal. Reconstruction, at least from the point of view of experimentalist, is ideal. Similarly, if I calculate Fourier coefficients in the expansion of top head coupling, I can calculate them analytically as a function of relative coupling radius sigma. I obtain curves, some curves, and on top of these curves I show points which were obtained by this algorithm using input data from numerical simulations and of chimera states. Again, you see that distinction is almost invisible in this plot. So in other words, I would like to summarize that based on these examples, method works reliably for the parameters which I showed, but because of justification in the continuum limit, it is expected that it will work also for arbitrary system sizes. And now I would like to advertise another advantage of this approach. It can also work for reconstruction from partial observation. So namely, if instead of entire chimera state, you take effective frequencies and local order parameters only of randomly chosen subset of points in it. And yeah, in general, this problem of reconstruction from partial observation is quite complicated. I would like to tell you a funny story from Berlin, which happened 2 years ago. So some time ago, a photo was taken of some animal in Berlin, and yeah, the person who took this picture said that there is a lioness walking freely in suburb of Berlin. And yeah, this suburb was completely closed for several days. Dozens of policemen searched for this lioness. At the end, they looked more carefully at the picture and realized that this was not a lioness but a wild boar. So this is like an example what type of conclusions can be drawn from partial observation. Fortunately for the method which I introduced you here, this problem does not appear. So here is comparison of application of the method if I take smaller system size, like 2000 oscillators, and record effective frequencies and local order parameters of all oscillators, or if I take 4 times larger system, but record only every 4th oscillator randomly picked up from the array. And in both cases, I can reliably reconstruct parameters with nearly the same accuracy. So I promised to stop after 45 minutes approximately. Therefore, I come to my last slide. So here is a graphical summary of the approach which I advertised you, namely given a certain network of phase oscillators, if one observes a partially synchronized pattern in it, then instead of collecting all information about all phases at each time moment, one can calculate only some small set of time averaged quantities, like local order parameters, effective frequencies, and using statistical equilibrium relations derived from the continuum limit, one can reconstruct with certain accuracy model parameters like coupling function, natural frequency, phase lag. These results were published in recently submitted preprint, but at the end of my talk I would like to stress that the method is not applicable exclusively to chimera states, but it can be applied to any type of partially synchronized pattern in coupled oscillator networks. And in particular, several years earlier, with colleagues from St. Louis University in the US, Istvan Kis and his PhD student Michael Sebek, we applied similar approach to reconstruct parameters in the system of globally coupled phase oscillators, like Kuramoto-Sakaguchi type model. And moreover, in this paper, we also tried to apply this approach to real experimental data, which Istvan Kis, who is electrochemist, could collect in his lab experiments. And we showed that this method works also for other topologies. The third reference, which I put it here, is about continuum limit approach. And with this, I'm at the end of my talk, and thank you for your attention.
Questions? Questions?
What Anderson idea is to look for Fourier modes which are just the power of the first mode.
Yes.
But how are they sure that they have a solution of the Ott-Anderson equation? Because you said at some point where Z is a solution of
Yeah, so maybe I try to answer your question as I understood. When I apply this ergodicity property, I use only this structure of the Ott-Anderson ansatz. I don't use exact solution. Okay, I use its structure, like there is spatially independent amplitude and constant frequency omega in the continuum limit, but I don't need to know them. So if you take just these two formulas and insert them in the expression for ergodicity, you obtain already from this substitution statistical equilibrium relations.
how are they sure that the solution of dz dt equal a nonlinear object exists, right?
You mean, okay. You see, the right-hand side of this equation is relatively simple. It is a cubic equation. So z squared, z cubed. And I can write some kind of self-consistency equation determining this amplitude A of x and omega as functions of system parameters. And from this manipulation with formulas, you can kind of say that whatever solution of this form exists, it satisfies certain equations following from this integral differential equation. And solution to this equation exists because it has invariant, it has upper bound. So if you have initial condition which lies in the unit disk in the complex plane at each x, it will stay in the unit disk for all the time. So there is no blow up. I think your question was about PD things.
Any other questions? Yeah.
Is this so the numerical method, does this assume all-to-all global coupling, or can it be?
So here you see system is of non-locally coupled oscillators.
Yeah, but that means it's fully connected. It's a fully connected network, right?
Okay.
But is there a way to extend it to a non fully connected network? Because like here, for example, node 1 will interact with, or can interact with all.
Yeah, I can go one step back and you can check if your question makes sense. So, for example, if you have top hat coupling structure, then you have a regular network where each node is connected only to some part of its neighbors.
Yeah.
It is already not fully connected.
But
and method is applicable.
Can it be like non-local but not fully connected? So like maybe like a bimodal kind of coupling. Would that work? Like for example, I connected to my two direct neighbors, and then another one randomly very far away.
In this study, I didn't analyze more irregular structures because non-local coupling introduces some kind of regular structure. But one can propose a version of this method also for random networks. But then instead of space, one needs to use node degree as an analog of spatial coordinate. And then by applying a similar approach, one can reconstruct node degrees and natural frequencies. But of course, you can't reconstruct all links in the network because you restrict ourselves with the usage of order n amount of information about observed state. So you collect only effective frequency and local order parameter of each node. This is 3n real numbers.
At the end, you showed the simulation results with a subset of the nodes.
Yes?
And I think you said that they were regularly spatially sampled.
Yeah?
Is that important?
Yeah, of course. I was a bit cheating. If you sample like a rear part of this animal only, it is not enough to reconstruct the entire function.
The whole thing's symmetric, right? So you've got a lot more information about a small part of the system. So it does degrade.
Yes, of course, because the reason is, roughly speaking, as follows. Imagine that you want to reconstruct Fourier coefficients of certain function if you have only a kind of observation of a part of this function.
Any other questions? Okay, if not, let's thank Oleh once again.
Thank you.
And I'm sure Thomas wants to go to the pub. So if you want to join us down at Uni Pub, and I'm sure Happy will be around. And Oleh, we both be around down there for a little bit, so you can say farewell to them before they go on their trips, either trips around Australia or trips back to Europe. Thank you once again.
Thank you.
Next week, which room?
Which room one?
I would just
Yes.
okay, so then
Distance. It literally is a cone.
it's a distance graph.
Yeah.
Yeah, I was like on a continuous graph.
Yes, he was eating a coffee belly for 3 years.
Chimera states have a small solution.
Very nice.
Why is that true?
I'm at physics now.
I'm gonna go read the paper.
There is a paper.
This sounds like frequency
I put it
in,
already.
frequency
Oh, I
out.
see.
If I understand what you're saying, because I read the output, but I also read like a follow-up paper that was like,
Oh, yes, sorry. I,
And that's about 3 hours before we close.
yeah, no, sorry. I immediately